Okay, now we've derived this theorem. Now we want to prove it. And well, here I've listed some vital elements in the proof. So before starting on the proof itself, I'm going to talk a little bit about transversality and the start from transversality theorem. And well, the Pontryagin-Thom construction, well, that's also very, very important in the proof. But we'll get through that as I talk about the proof. So, well, first of all, the definition of transversality. Well, here we have the definition of transversality that is given in Andrew's book. And I first define for you what transversality means. So I'll write down here in the board a definition of transversality. So let's consider M and N the two submanifolds of W. Well then, we say that M intersects M transversely and we write this is the notation for that. If M intersects N transversely, we write it in this way. So we write it as in the way if at all points X in the intersection of these two manifolds, we have that the tangent strings whether the section is empty if so this here is the definition. We can draw this with a nice picture. It's very easy to see from a picture. And well, it's in Patrick's web page, you can click on some nairspace spheres that define transversality exactly in this way. So I've stolen his pictures, and that's what we're going to see now. So suppose this is the manifold N, and this is X. This is manifold N. So these two manifolds are transverse, but here we are in R2. Sorry, R3. And well, now an example of non-transverse. N. N. So these two manifolds are transverse, and these two aren't. If you see this tangent space here, which is with the definition. So this is a definition of what it means that two manifolds are transverse and non-transverse. What we have in Andrew's book is that definition, and well, if we consider a map G between manifold N and the down space of that bundle that you have over there, it's an R bundle, then it's very important to define what it means for the map G to be transverse? Well, G is transverse at the zero section of that vector bundle if the inverse image of that zero section is a submanifold. So I'll erase this. So what the definition is saying is that we have G, a map from M to the some space of a vector bundle. And it also says that the vector bundle is where you have it there on the slide, it's an R bundle, and that X is the zero section. So X is a submanifold in here. So what it means, and it's vital for the proof of the Tom's theorem. It's very important. What it means is that the inverse image under G of X this inverse image is a submanifold of M. It could not be. It could be the case that this inverse image isn't a manifold, but then G wouldn't be transverse. And well, the dimension, the fact about the dimension is quite obvious, because then we are making this a manifold of dimension n, which is the dimension of n, minus the dimension of the well, it was an R-plane bundle, so that is what this R here means. And well, I think that's all that I need to say about transversality, but it's a really important concept in the proof. Now, another of the vital ingredients in the proof is the Sarton transversality theorem. Well, again, I am quoting the theorem just as we have it in the book. And well, what the theorem is saying is that if we have any map that we can imagine from an n-dimensional manifold to the Tom space, then we can make it homotopic to our map G from the previous slide that we already said it was transverse. So that's really fine, because we can make any map F transverse or not. We can homotopy it to become a transverse map. So that's really important. Well, and now for the proof. Well, I am going to be denoting we want to show that this is an isomorphism, that the co-Bodism groups are isomorphic to these stable homotopy groups. So we want to show that this map is an isomorphism. So this is going to be denoted, I'm going to denote it by big theta. And to show that it is an isomorphism, I'm going to split up the proof into 4 different steps. First of all, I need to see that they in fact have an element of this stable homotopy group. Because if we don't find an element, then we are in trouble. After that, we need to see that it is in fact a homomorphism. But if we have an element and we have that it is a homomorphism, to show that this homomorphism is in fact an isomorphism, we only need to show that it is a surjective map and it is also injective. So that those are going to be steps 3 and 4 in the proof. So first of all, we want to show that the map is well defined, and we need to describe an element in here. So we first are going to consider a co-Bodism class in the co-Bodism group. So this is going to be denoted by M brackets. That's the usual notation for a co-Bodism class. And then we are going to let I be an embedding that embeds the manifold. We choose a manifold M and embed it in R dimension n plus k. Well, by the Whitney embedding theorem, we know that we can do that, and we have been meeting in the first part of the talk. We have already met the classifying map of the normal bundle that we had before. Also some more notation. We're going to use pi for the projection between the total space of the bundle and the manifold M. So that's notation. Okay. So what we first do is that we choose a tubular neighborhood of M. Just think of a sort of a framing. And then we are going to write this R of dimension n plus R union infinity. We're going to consider also the infinity, and we're going to write this as the n plus R dimensional sphere. And consider this map. Well, what is this map doing? The map, what it does is just well, it leaves the tubular neighborhood untouched, and all the rest of the sphere, and also of the boundary of this tubular neighborhood, it collapses it to a point. And that should sound familiar, because that is exactly the same as what the Tom spaces map do.